So I would have my my y-axis and my x-axis, something like this, and then I'd give you this graph. And as you guys saw maybe on your calculator, the graph looks like this. Starts there at the origin, kind of goes up, and then does that. That makes sense? So then the line x equals 3 would be right about there. And we'd have our lovely region right in there. That makes sense? So I'd give you a graph like that, and then we'd go from there. So if you remember from before, this is from back in early chapter 4, to find the area between the x-axis and a curve, you're going to set it up as a definite integral. And the definite integral would accumulate from 0 to 3. It would just accumulate across that interval. So I'd say definite integral from 0 to 3. And then what kind of a thing goes inside the integrand? What are we talking about? Like what? Maybe this will help you make a connection. Say again? Not a rate, because we're not looking like... Yeah, y is not really a rate. I suppose we could maybe sort of make it look like that, or we could think about it that way, but I'm even thinking more general. Say again?
Like the output?
It is, but the question is why? Like WHY. Like, why would it be that? Like, is it just this magical thing, or what's...
It's like...
Let me draw something in here that might help. You all have done this. At this point, you guys have done this a bunch, right? Little rectangle, another little rectangle, all that kind of stuff.
We're just getting all the y values for between 0 and 3.
We are, because what do the y values mean for the rectangles? The height. Okay, so if I put this in here, here's my y values, x over x squared plus 1. Those are all my y values as I move across this region. But then what do we always multiply by that sometimes we forget to multiply by? The base, which is? That's the height of the rectangle. What's the base? Dx. A little tiny change in x. And so when you stop and think, I hope, this should make sense. Basically all this is the definite integral of height times base.
Why is that the base?
Y is what?
Dx, the base.
So dx stands for, so dx kind of looks like delta x, right? And delta x means a change in x. Dx means like a little itty bitty tiny super micro change in x. But it's still sort of a delta x. So if I were to look at this base that I am coloring a lovely orange color, you see it? So would you agree with me that the length of that base is simply whatever that x coordinate is minus whatever that x coordinate is? That would be the length of that base. So if I take an x coordinate minus another x coordinate, isn't that a delta x?
Yeah.
And since the definite integral is saying, yeah, we have delta x's and everything, but we want those delta x's to get closer and closer and closer and closer to 0, so we can have an infinite number of them, and all of a sudden dx really is your base. Like this little space in between the edges of the rectangle is your dx. So that's your base length of your rectangle times the height, gives you an area. The definite integral is simply going to accumulate those all the way across the region and add them up and give you the actual area.
So why is it dx in our delta?
That's a symbology issue, right? So if you wanted to put a delta x there, like anybody that really knows calculus, they would understand what you're saying. But Leibniz, the German guy who developed calculus, he kind of started with this idea of delta y over delta x. That's our standard slope of some line, right? Or secant line slope of a curve. But he wanted a different notation that expressed, you know what, it is a delta x and a delta y, but we want those delta x's to get really tiny. And so he just said, you know what, let's call it a dx. Like a delta starts with d, right? So like capital D delta is like potentially a large change in x, but small d, lowercase d, is a little itty bitty tiny, almost getting closer and closer to 0 change in x. So it's just symbology. I would say it would be like if a younger student said, you know, like if you were tutoring some kindergarten or something, and they said, Bailey, that means A, and that means A. That doesn't make any sense. And you'd say, well, one of them is a capital A and the other one is a lowercase a. And they have these different implications. That's all it really is. It's just a symbology issue. But there is a story behind it. Yeah.
Actually, I'll just wait till you do it.
Okay, fair enough. So all we have to do now, we have this set up. All we have to do now is try to evaluate this. We're going to do this not with the calculator. We're going to do this paper and pencil or iPad and Apple Pencil. I'm going to ask myself the question, is the derivative, it's a fraction, so is the derivative of the denominator the same thing as the numerator? What do you say? What's the derivative of the denominator? And the top is just an x, so as we've said before, Timmy has once again messed it up, but not that bad. How do we need to change the numerator? Oh, how do I change the numerator? Did you say multiply? Okay. Multiply by 2, and then on the outside, divide by 2, right? So now Timmy's issue is completely fixed, and we have a lovely chain rule fraction, which will lead to a natural log. So the antiderivative for this would be 1/2 natural log of the denominator. Don't forget the absolute values. And then that's evaluated from 0 to 3. Again, just a reminder, sometimes I see this. Please note that at this point we've done the antiderivative, so the tall, skinny s should be gone because we did the thing that it was telling us to do. Now I just need to do FTC1 and evaluate. So this would be 1/2 ln of 3 squared is 9 plus 1 is 10 minus 1/2. 0 plus 1 is just 1. If you left it like that, it's perfectly acceptable. It would be so awesome if you knew what ln of 1 was. 0. So the final answer here would just be 1/2 ln of 10. And you would be even like a 1/2 degree more awesome if you knew how to manipulate this and make it look a little bit different. So, now ln of 10 over 2, it is something to do with 1/2, of course. What could I do with that one?
ln of root 10.
Oh, there's that 1/2 more degree of awesomeness. 10 to the 1/2 is really square root of 10, right? Let's just be honest about this. This is perfectly acceptable. This is perfectly acceptable. So is that. There is no need to go to the final green box. It just was more of a fun fact. If you remember those, that might be helpful on WebAssign potentially. But that's just going back to those old log rules that you learned like in pre-calc or algebra 2 or both, something like that.
Wait,
Anna, your question?
so you just plugged, like after the one above the green box, you just plugged in.
Yeah, I plugged in the 3. I did FTC1.
Okay.
Yeah, 3 squared is 9 plus 1 is 10.
Okay.
And I subtracted the evaluation at 0.
Minus ln. So how do you, oh, you know the ln of 1 equals 0.
Yep. And 0 times 1/2 is 0. So,
If you don't count us off, we don't put the absolute value.
so WebAssign most assuredly will. At this stage, I'm willing to accept that you're in process. And so for the most part, as we go through this, I'm not going to be like looking to take points off for that. But please know that it should be there. And it will, when we get to chapter 6, which is next after chapter 5, it will absolutely matter. And so what I'm trying to say is I want you to get into the habit of doing it, but I'm not going to like look to just like ding you on points repeatedly right now because you didn't do it. I'll probably, like say you take a quiz, I think there's one next week, maybe on Tuesday or Wednesday I think it is. If you were to write your answer without that, I'm not going to be looking, again, I'm not going to be looking to take points off, but I'll probably write them in there and say these need to be there. As we start to move through, then I'll start taking points off if they aren't there. But you're in process now, so.
So if you like wrote the 1/2 ln and then the absolute values, but when you plugged in the 3 and the 0, you dropped the absolute values?
You totally can because 3 squared plus 1 is 10, and the absolute value of 10 is 10.
Okay, so that,
So it's
Okay.
just when it's like a
so that's
It's only when there's
fine.
variables in there. Yeah.
Technically, couldn't you drop it before because
X squared plus 1 could never be negative, or 0 for that matter. You are right. Yep, you are totally right. So this is a good example of where the absolute values really should be there, but when you think about it, they aren't really necessary. And so like when you get into chapter 6, that would be a good observation to make, for sure. Anyone else? Okay, everybody stand up real quick. Literally. To your feet, everyone. Please. This will be your slight exercise portion of the class. I want you to switch seats, switch tables completely. You guys over here, you guys over there, go. And sit down. No, just leave your stuff where it is. It's like musical chairs, except I'm not going to take the chair away from
Oh, we
somebody.
gotta switch like completely, like switch. Oh, okay. Switch sides.
And I think it makes a lot of sense. I do want to tell you that this topic is one that I used to really hate, not because it was like a bad topic, but because the symbology of it all really got in the way of my students understanding it. And so I really felt like I would spend like a day on this or a class period on this, and my students would never get it because, like I said, the symbology was a mess. And then somebody talked to me about this one time. It was like, it's been like 15 years, and they said, well, here's how I do it. So like any good teacher, I saw something I liked, and I just stole it, and I still use it. And it's turned from something that I really didn't even want to do because my students were just like, what? I get so confused with this and that and the other thing, to something we'll cover here in the next 20, 30 minutes. And there will, of course, be a little discomfort at first. By the end, you'll be like, oh, that's sort of easy. And it'll be the type of thing where you see it on a quiz or test. It'll almost for sure be a guaranteed win instead of a guaranteed loss. Yeah? Okay, so here we go. Let's remember.
Yeah, now I'm gonna feel really bad about myself when I get these wrong.
Everybody's going to get one wrong at some point. That's okay. The point is you'll eventually get it. This is a much better method. I wasn't setting you up for anything other than this is better than what most textbooks will teach. Okay, so let's look at some properties of inverses. These are things that you may or may not remember, and if you don't, that's fine. I'll remind you of these, but hopefully these will make sense with what an inverse is. If we look at this first statement right here, G is the inverse function of F. So G and F are inverses of each other if the composition F of G of X, so in other words, a composite function F of G of X equals, this might be something you remember from pre-calc or not, I don't know. Do you guys know what would go in the blank?
Isn't it G of, no? G of X.
F of G of X. Think about what an inverse does. Doesn't an inverse strip away everything that the other function did?
Would it be G of X? Or F? Zero?
No? What's the input? The input, well,
Or X.
what is the
So would it just be X?
tiniest input is X, right? So if F and G are inverses, wouldn't F and G do battle and kill each other?
So it's just X.
The leftover would simply be the input, X. So if F and G really are inverses, whatever F did, think about it like this. If they really are inverses, whatever F did, wouldn't G exactly reverse it? Leaving you with simply the input. And if you took the composition and you did it the other way, if G and F really are inverses of each other, then the reverse composition would work exactly the same way. G of F of X would equal just the input, X. That is certainly a key characteristic of inverses. We will use that to help us with this. Okay? And then the other one might be a little bit easier to remember. It can also be said that if two functions are inverses, the blank and blank are exchanged. Inputs and outputs, yeah. So if F and G are inverses, then the inputs of G would be the outputs of F. And the inputs of F would be the outputs of G. They just get switched around. Inputs and outputs get exchanged. So these two concepts regarding inverses, and there are, as you guys know, perhaps in the back of your mind, there are some other characteristics of inverse functions. These are the only two that we really need to know to help us be successful. Make sense? Think about the word inverse. Hopefully that'll help. I thought I'd illustrate this a little bit for you. F of X equals X cubed plus 1. I thought we'd do a little table of values and do a little comparing. So if you would, maybe off to the side here, let's look at a table of values for F of X. Let's do 4 of them. Suggestions on inputs. 0 is always good. How about a negative input? Maybe negative 1? Let's go above 0 now.
1.
Positive 1 then? Okay, let's do it. So let's go input, output for these. I'll do the same thing. I'm going to do one more random one.
7.
Oh, 7. I like it.
Did you just do that in your head?
I'm a math nerd.
I did it in my head.
I've been a math nerd for a long time. Some things stick. 7 cubed. 343. Yeah. Okay. Okay, so this very algebra one of us, right? We go input, output, input, output, input, output, right? Okay, so let's do the rest here. It says, find the inverse of f, and we'll label the inverse g. So let's do this right here in the middle. So I'm going to, you guys remember, like if I've got y equals x cubed plus 1, do you guys remember how you actually find an inverse?
Switch the X and Y.
Yeah, use that second principle, take your inputs and outputs and switch them, and then solve for y.
Oh,
So-
with the table when you just like.
We're going to see it illustrated, yeah. So there, I've flipped the inputs and outputs. The x and the y have been switched. Then I'm going to solve for y. So this would be x minus 1, blah, blah, blah. Okay, so this is g of x, and that's my inverse function, right? So I labeled my inverse function with g. We'll be consistent about that. Okay, so we're going to be a little more strategic about our inputs here. Knowing what we've just been talking about the properties of inverse functions, what would you guys propose for intelligent inputs for G?
0, 1, 2, 9, 3.
Yay, there we go. 0, 1, 2, that makes a lot of sense. 9, where'd you come up with that? 344, what in the world? Of course, she's just using the outputs for F to be my inputs for G. We'll see how this goes. So if I take my G of x function, and I plug in a 0, I get 0 minus 1 is negative. Oh, can I do the cube root of a negative 1?
Yeah.
Yeah, you can. You can do an odd root of a negative. You can't do an even root, but you can do an odd root. So, sure, cube root of negative 1 is negative 1. Wow, interesting. When you plug in a 1, what happens? 0. You plug in a 2, what happens? You plug in a 9, 9 minus 1, you get a 2. And then you could amaze people. Oh, 344. Oh, of course, it's 7. Duh. Everybody knows that. And you can see here, right? Can you guys see how the inputs for F were the same as the outputs for G? And the outputs for F were the same as the inputs for G. So I just wanted to illustrate how these inverse properties kind of go together. Question?
For notation, so I know that in the last section, or like when we were talking about derivatives, and so it's like G, when we had like G of x equals like the definite integral of f of t.
Yeah, sure.
Well, so how do you, I can't remember how you say like f of x, like the G of x is the inverse of.
Oh, like the notation for that? That is actually going to be, we're going to talk about that next, but let's talk about it now since you brought it up. This is a good notational thing. So this is actually one of the core reasons why I like doing it the way I do it now instead of the before. So it used to be that we would say that the inverse of f is f with a little minus 1 up there. So that's kind of the, if you look at your calculators, that's a pretty standard way of writing an inverse. Here's where we run into issues. If I wanted you to find the derivative of the inverse of f, wouldn't that be this? And this single ugly notational stuff is the exact reason Ah Young's look on her face says it all. She's like, people get confused, and I totally get it, because then eventually what does this thing do? It starts moving around. It looks like an 11. Or does the prime come before the negative 1? And people have a hard enough time remembering what the negative 1 means anyways, right? And so all this symbology with all these extra little tick marks and a negative 1 made a mess. And so I understood, like, my students, because I wasn't necessarily confused myself, but I could totally see why they would be, because they're like, we just learned this whole negative 1 thing last year. Now you're putting this extra little mark there, and we got to keep those two things straight? It was a mess. So what we're going to do, if we ever run into this notation, we are going to instantly say, I really don't like that. I'm going to just say that the inverse of f is the same thing as g, and I'll use g to represent the inverse of f, and that way there's not all these extra little tick marks and the minus 1 combined, making one big mess that we don't even really know what it means. But if you know g is the inverse, you just keep that in your mind. The little tick mark just means derivative, and that's it. So notationally, it just makes it easier. So thanks for bringing that up.
On the AP exam, can we use that?
Yeah, in fact, most of the time now, in the last like 5 or 10 years, the AP test has started to set you up for success by saying, hey, we're going to call the inverse G. Now find this or find that. College Board, they're adaptable. They are very adaptable people. Okay. So then, the other piece to this puzzle that I really didn't like, that I needed to do some thinking to get past, was simply this, that the way that it was presented and the way that it is presented in most textbooks is, hey, here's a formula involving primes and negative ones up there in the exponent looking thing, and hey, student, just memorize this formula. And it was like, whoa, what if they forget? What are they supposed to do? And the formula has minus ones and primes, and on a bad day, I feel confused too. And so how are they supposed to do this? So I wanted to show you where this comes from using properties of inverses. So if you are having a bad day, maybe you could remember one property of an inverse and get this on your own instead of like just memorizing it. You're welcome to memorize it, and I hope that eventually you do use it enough to where you have it memorized. But I want to show you where it comes from, okay? So let's think of it like this. We're going to use a very specific property, and it's this. I'll put it like this. If the inverse of f equals g, we'll start off with that proposal that we're going to call the inverse of f g, just for sake of notation. And I took a composition and I said f of g of x. In other words, I plugged g of x in for the input of f. Based on the properties that we talked about a few minutes ago, what would the result of this be? X. This is where we're going to start. If you can remember this one property, you can get to this derivative and be in pretty good shape. Let's remember this right here. We're looking for the derivative of the inverse. And so in the end, would you guys agree with me that our end goal is to find g prime? We're trying to find the derivative of an inverse function.
Why aren't we just finding?
Oh, I was hoping somebody would ask that. You're going to find out in a second that finding inverses, not always easy. In fact, I would say not always possible. And so
would it be easier to find g prime and then do the next one?
you're going to find almost always going to be easier to do what I'm about to show you. Yeah. You're going to see it right away on number one. Okay, so here's how this works. If I'm looking to find g prime, and I've got this lovely relationship right here, what would you guess I'd need to do? Find the derivative of that. So what I'm going to do is I'm going to do ddx of this equation, ddx of both sides. Let's start off with the right side, because that right side is going to be super easy. What's ddx of x? 1. Okay. So 1. And then on the right side, whenever you do ddx of a composite function, what rule do you have to use? Chain rule. So think for a second, see if you can do this. We've done this before. What would it look like to do the derivative of f of g of x using the chain rule? Does that make sense? Derivative to the outside with the little box still in there times the derivative of the little box. Technically times 1, right? Because you'd be doing ddx of x, but usually write that. Remember, our goal was to find g prime. Do you see it? What do I need to do to get it by itself? Just a little division, yeah. So it'd be g prime of x equals 1 over f prime of g of x. And so that's our relationship right there. So we can derive that derivative relationship, be in pretty good shape. No. We have a little trick up our sleeve. Based on properties of inverses. We'll get that in a second. So that's the relationship you either need to be able to arrive at quickly or have memorized, or if you're having a bad day, do that real quick, derive it real quick. So I just wanted to show that to you so that you'd be hopefully equipped to do that if an emergency comes up. But I'm hoping if you do enough of your homework and you're practicing, remembering it will be not much of an issue. So that's just a property. It's understanding what the word inverse means. Like if I said, I am the inverse of you, that means whatever characteristics we think of in regard to you, I would be polar opposite. So G simply undoes whatever F did. F undoes whatever G did. Right? So, it's like when people exercise for an hour and they're like, I just burned 700 calories, and then they eat a large pizza. Those are inverses. Right? So, yeah, so if F and G truly are inverses, they're going to completely strip away everything about each other, and the only thing you're left with is the input. Whatever G did to X, F's just going to come right back in and undo it. So it's more of a philosophical discussion about the word inverse than anything else. Okay, let's do some examples. So take a look at number 1. Like I mentioned, number 1, you're going to get a good look at this right away. So notice number 1, it gives you this lovely equation for f of x, and then it gives you some direction. It says find the derivative of, and you kind of have to know what that notation means. It means the inverse of f. And we all like do a little gagging like, oh, why do they have to choose that symbol for inverse of f? They have their reasons, but we don't like it. And so whenever we see something like this and we realize, we're going to be trying to find the derivative of the inverse of f, we're going to immediately respell inverse of f with what letter? G. And we're going to write that down. We're going to say, you know what? I would prefer to write this. And since I'm relating those two things like so, I can use one for the other. So the inverse of f, we're just going to write it down as G.
So we need to write that on the...
Yeah, you want to. If it hasn't already been done for you. Because if you think about it, if you just start writing G all over the place, they're going to be like, what is that? I can see F, I can see inverse of F, but you started writing G, whatever.
I just see those at least kind of like a...
I think it's starting to get a little more, yeah, it's getting a little more typical, I think. But you'd want to write it down for sure. Okay, so let's start off with that relationship. So if I'm looking for the derivative of the inverse of F, and I've defined inverse of F to be G, I'm going to be looking for this. G prime, I'll put it like this. G prime of X equals 1 over F prime of G of X. That's that relationship we just derived a few minutes ago. Make sense? Now we're not looking for just the derivative of the inverse of F. We're looking for the derivative of the inverse of F at X equals 3. So what does at X equals 3 mean? Plug in 3. Yeah, wherever you see an X. Sure, G prime of 3. So G prime of 3 equals 1 over F prime of G of 3. And this is where Anna's question comes into play. This is where it gets interesting. So G of 3. Wouldn't it be so lovely if we had a function for G? In other words, like G of X equals blah, blah, blah. Wouldn't that be awesome? Because then we can just plug in a 3 and we're done, right?
Why can't you just switch?
So Anna proposed this, and this, I think this is potentially a good idea. Please don't write this down because you'll just erase it later. Just watch.
So it's not...
If we had this, and Anna said, well, why couldn't we just swap the x's and the y's and get the inverse?
And then plug in 3.
Sure. So here's the problem.
You can't solve for y.
Oops. Take that and good luck solving for y.
That's easy.
Seriously, unless you've taken like modern algebra or abstract algebra as like a college or a graduate course, you don't have a prayer of solving anything like that. Not going to happen, right? So, and even then you wouldn't really get something that would be all that usable for us. So, in other words, you can't. So we're going to use a little trick though, and it's going to be based more or less on what you're talking about. So let's think about those properties of inverses. Remember, one of the properties was f of g of x equals x, right? The other one was, and we proved this, that the inputs and the outputs get switched. So listen carefully. If I'm looking for g of 3, I'm basically being told, make the input for g 3. Right?
You need to find the output.
So the inputs of g would be the same thing as the outputs of f. That makes sense? The input for g would be the same thing as an output for f because we know they're inverses. So what I would do, I have got a function for f. Instead of plugging a 3 in for x in f, I'd plug a 3 in for the output of f.
That's kind of the same thing, but you would have just plugged in 3 for x.
Exactly. I like this notation better though without the swapping because it keeps us consistent on our inputs. So remember, an input for G is the exact same thing as an output for F. Now the question is, how on earth would you solve something like this if you didn't have a calculator? This can be the one time I say this year. Believe it or not, guess and check. I'm not kidding. Guess and check. The good news is, it's not going to be one of these situations where I'm like, I'm sorry, Alex, you didn't guess 17/9 pi. You don't get it. It's not going to be some obscurely weird number like that. It's going to be something like 2 or -1 or 3. It's going to be right around 0 somewhere. And so, for goodness sake, don't start out by guessing, gosh, I wonder if x is 111/17. I don't know. Start off with how about just like a 1 or a 2 or something? So, hey, use your powers of guessing and check. I bet you've got it. Think it over. What do you guys think the x would have to be? 2 is right.
Sorry.
No, you're good. So we would say x is 2. And so this is equal to 1 over f prime. What's g of 3? 2. So I can replace the entire g of 3 with 2. And now the good news is I do have a function for f. So finding f prime is actually pretty easy. F prime would be 3/4 x squared plus 1. So finding finding f prime of 2, I get 4. So my final answer would be 1/4.
And so would you write just 1/4, or would you have to write like f of -1?
So the good news is I've connected inverse of f with g, and I've connected g prime of 3 with my answer, so I wouldn't have to do anything extra with that. Like everything is linked. I'm saying the inverse of f is g, okay, g prime of 3, which would be the derivative of the inverse of f, and I've linked everything with equal signs. I wouldn't need to do anything additional. There wouldn't be anything wrong with what you're describing, but because I was careful.
Like all linked together, you just want us to write g prime of 3 equals 1/4?
Yeah, as long as you've linked the two of them, there's no reason you couldn't do that. In fact, I think there's a reason you should, that notational stuff, right? Eden.
We help for inverse functions, you had to prove that the inverse function existed, right?
Oh, with the one-to-one?
Yes.
Yeah, we're not going to do that.
So you, okay.
Think
We're not going to mess with one-to-one stuff. I'll give you things that are one-to-one. The horizontal line test, I think is what you're talking about. Yeah. Okay. All right. So let's see if you guys can handle number 2. This will be our final one for the day. I think that'll leave us 1 for tomorrow. We'll get this all wrapped up tomorrow for the week. Let me show you an answer. What do you guys think? G prime of 7 equals 1/6. You can see in the middle there, I found my input-output switcheroo, got that settled, and then found my derivative, and then plugged in the 1 for that. Okay, so that's our time. We'll do that last one as kind of a warm-up tomorrow. Sorry we didn't get to the intro video material today. I forgot that we had that left over from 5-2, but we'll be on track after tomorrow, I think. So tomorrow is all about E. Yay. Have a great day. See you guys tomorrow.
Yep.